Data representation for semantic environment perception is crucial in autonomous driving. In recent years, semantic bird-eye view grid maps have attached increasing attention in robotics research community. Compared to the front-view semantic segmentation images, semantic BEV grid maps are more straightforward to use. In semantic BEV maps, a geometric relationship between ego vehicle and obstacles are explicitly illustrated in a neutral way. This advantage makes them more suitable for downstream tasks, such as motion planning, trajectory prediction, etc. In addition, many of those downstream tasks are trained with visual images in simulation environments. Since simulation environments lack real textual details compared to the real-world environment, here is a great domain gap lying between the real and the simulation environment. So we choose to generate a semantic map to alleviate the domain gaps. Most of the existing end-to-end methods adopt supervised learning to train their network, which require a large amount of ground truth images to achieve acceptable results. The dataset with hand-labeled ground truth for semantic BEV grid map are limited. In addition, manually labeling images is tedious and label-intensive, and manually drawing semantic BEV map according to the front view camera images is difficult for humans. To address those issues, we proposed a semi-supervised semantic bird-eye view grid map generation network, also named S2G2. Now we'll go through some details of our S2G2. This figure shows the overall architecture of the proposed S2G2. We aimed to generate a semantic BEV grid map in a semi-supervised manner. Our S2G2 mainly consists of a feature extractor, a dual attention view transformation module, and a double branch generator. During the training, we first feed the labeled and unlabeled images into the feature extractor and get the front view feature maps. We use a pre-trained CNN module, which is EfficientNet as our feature extractor. Since the EfficientNet has various variants, we conduct an ablation study on the different variants. Through experiments, we choose efficient B4 as our backbone. The dual attention view transformation module performs the view transformation based on the circle consistency and then refines the BEV feature through a design dual attention mechanism. To train the view transformation block, we introduced a circle consistency loss to make a reconstructed front view, which is the F front hatch in the figure, being similar to the original front feature, which is F front. Here we'll show the inner view attention block, and this block enables our network to focus on both spatial attention and channel attention of the input BEV feature map. The two types of attention are extracted sequentially. In order to make the inner view attention and the cross view attention complementary, we introduce the BEV loss between the output of the separate attention blocks. This module maintains the same dimension in the input and the output feature maps, so it can be inserted into any existing network seamlessly. To verify the effectiveness of the dual attention block, we conduct two groups of tests with and without a certain attention block. According to the results of the previous ablation study, our network got the best performance with the EfficientNet B4, but EfficientNet B7 is the most complicated variant with the most number of parameters. It should perform better, so we choose the B4 and B7 variants as our feature extraction module to conduct this ablation study. From the table, the dual attention that combines the inner view and the across view attention together get a superior performance against its counterparts. After the dual attention view transformation module, we can get two distinct BEV feature maps generated from inner view attention and cross view attention separately. Here we denote those two BEV feature maps as homologous features. To achieve semi-supervised learning, we developed the double branch generator as the last module in our S2G2. This module takes the homologous features as the input for the passive branch and active branch. Given the similar output, the two branches should generate consistent output. Here we conduct an ablation study to determine the best input order to the double branch generator. To make our network acquire the ability to output similar prediction for homologous features, we introduce a consistency loss that calculates the differences between the prediction from the active branch and the passive branch. At each training step, the active branch updates through the gradient descent from the weighted sum of the segmentation loss and consistency loss. The weights in the passive branch are updated with an exponential moving average strategy instead of the gradient descent manner. Two hyperparameters gamma and R need to be set during the exponential moving average update. The figure below shows the parameter adjustment process. For more details, please refer to our S2G2 paper. Here we conducted our experiment with the modified cityscript dataset. We processed the dataset by combining the labeled and the unlabeled image together as the input of our network. According to the different amount of unlabeled image in the training site, we conduct our experiments with three different sites, which prospectively include 10%, 40%, and 80% of the unlabeled images. As our S2G2 is the first method that generates the semantic BEV grid map in a semi-supervised manner, we developed several baseline methods to perform the competitive experiments. We also evaluate the performance of our S2G2 together with some of the state-of-the-art supervised learning-based methods. Both experiments results demonstrate the superiority of our network. Here we show some sample qualitative semantic BEV generation results. From this figure, we can see that our S2G2 generates a more precise and clear semantic BEV grid map. The last two rows display the more complicated driving environment due to the unusual road conditions and the uneven sunlight. Most of the other methods fail to predict the correct semantic classes, but our S2G2 still provides relatively clear and accurate semantic boundaries. Here we show more predicted results from our S2G2 and other state-of-art methods.